Hello, class. I just spent about 35-40 minutes giving you a great lecture, and then unfortunately realized that the size of the lecture would be I tried to go with high definition because I'm trying to set up two cameras now rather than just the one camera, so that you can not only see what I'm writing on the tablet, uh, like I did this summer when I finished, or the spring when I finished up the courses there. But now that they've sent me out a second camera, yes, it's only taken 3 months. But I finally got the second camera and I've set it up. And then I tried to run that high definition and it came out to like 600 megabytes. And if I'm going to upload that on YouTube so that you can access that no matter where you are, and with whatever type of computer you've got, then I have to keep it less than 128 megabytes to upload it to the Scott Grenquist channel at YouTube. So I did that, and I did a lecture, which would have been the second lecture in the series. The first lecture in the electromagnetic field theory class is already up there. It's at a YouTube channel called Scott Grenquist. Pretty appropriate, right? So if you type my name in, Scott Grenquist, to YouTube, channel's going to come up. Now, it's got a lot of things on there for AC network theory, which is another course that I taught in the spring. But it also will have lectures listed numerically for electromagnetic field theory. And the first lecture for electromagnetic field theory is already up there. And that is on James Clerk Maxwell's equations, and how those equations and how his epiphany, right? You've got to remember that, like, one night. Now you've also got to remember that Einstein gave all the credit for his discoveries to James Clerk Maxwell rather than Newton, which is what one person, recommended. He's the new Newton. No, I'm the new James Clerk Maxwell. And he owed it all to James Clerk Maxwell. Oh, he's right. One instant, one night, James Clerk Maxwell sat down there and he thought, God, that looks just like the velocity equation, the second order differential velocity equation. And you're probably thinking, what the hell is the second differential equation? You're right. Who would have even known those equations and really understand the deep mathematics at that point? I think a lot of people could have, had they also had that relationship with Faraday and an understanding of what was going on in Faraday's laboratory with electricity and magnetism, and understanding the thing between the relationship between those two. So anyway, getting back to the point, I already did that lecture, and you've got to watch that lecture first. I am doing this lecture now on dimensions and units, and we're going to redo the lecture, but hopefully this time it's only going to be like 75 megabytes. And I think that everybody can still see. I've been trying this. I spent like 3 or 4 hours this morning to try and get this system set up correctly, so that as we move through the course, we have about 20 or 30, 25 to 30 of these lectures, in addition to homework, in addition to tests. I think that I'm going to probably limit the tests to 2 tests and a final examination this semester. So we'll see. I'm flexible, but that's probably what I'm planning to do. It is a rigorous course mathematically. I'm going to tell you that right now. You're going to learn more mathematical principles in this course that are going to hold you in good stead in your discussions, communications with other electrical engineers throughout your lifetime. Well, that's right. I don't have the mirror image on, so I'm actually seeing me as you see me. God! All right. Now, let's get to the lecture, because like I say, this is just a review lecture for most of you who have had me before in an understanding of the importance of dimensions and units. And I want to stress this, that 85% of all engineering errors that cause loss of life sometimes occur because of a misuse of units. Units and dimensions. So understand units and dimensions. That's really the good, the thing that separates really good engineers from not that good of engineers. All right, so let's get stuck into it. Let's get back and switch cameras. There you go. So I already did this lecture earlier, and so what I want to do is I want to go through the lecture again. And like I say, it's a review lecture, and the reason I made it that review lecture is in case something like this happened where I tried to do it in high res and it didn't work out, I could always fall back. Now, I'm going to point this out down here. This is where I spilled my eggs all over our whiteboard. But so I circled it, so nobody step in that. Okay, primary units. Let's get back to those. Now, the primary units, as you know, with the dimensions and the unit, length is in meters, time is in seconds, current is in amperes, mass, kilograms, temperature, degrees Kelvin. Now, I'll mention a couple things here. Degrees Kelvin is not how it's pronounced. It's really pronounced kelvins. They thought that they just changed the whole concept of temperature overnight. And instead of calling it degrees Celsius, degrees Fahrenheit, degrees Rankine, they would call it kelvins after Lord Kelvin. Well, I can't do that. I think it's degrees Kelvin, and so I'm going to stick with degrees Kelvin for the rest of my life, and then after I die, your generation can call it kelvins if they want. The sixth one is illumination, and there is a difference between illumination and luminosity. Luminosity, of course, is in lumens, and illumination is in candelas. I'm not going to really go into the difference between candelas. We will be looking at, if we get to that end point where we start to look at fiber optics, I think we will. Fiber optics and an introduction to fiber optics in this class, and transmission of information over fiber optics. We might be looking at some aspects of that, the advanced aspects, where we're starting to talk in terms of candelas or lumens. I don't know how far we'll get with that. So let's just see. There's a lot that falls under electromagnetic field theory. But the critical part here is that we start to look at, of course, Maxwell's equations, because that is electromagnetic field theory, A. But to get up to Maxwell's equations, we have to look at electrostatics. Up to this point, there is no course that I know of that has taught you anything about electrostatics. And you're probably saying, well, electrostatics, what's that? Well, electrostatics is why we've got 3 wires, right, running over the top of us, power wires. And what are those 3 power wires doing up there on those high tension power lines? Three or four, they're different configurations. But really what they're acting as is a waveguide or a conduit to allow AC voltage waveforms, voltage and current waveforms, to travel over those high tension lines, right? And so that's what we're going to be looking at too, is transmission line behavior, antennas, and so all of these different things that are associated with electromagnetic field theory, to give you guys as good of an understanding as you possibly can, both at the technical level and also, when I say technical level, I mean at the mathematics level, because that's what separates us engineers, and also at the applications level. All right, so let's go through this. And another thing I wanted to point out besides that was that the SI system comes in 2 flavors. It comes in the MKS flavor, which is meters, kilograms, seconds. But it also comes in the CGS flavor, which is centimeters, grams, and seconds. And you're probably thinking, well, do I even have to worry about that all that much? Because everything's going to be changed over to MKS. I'm never going to see this CGS thing. That's not true. When you go back and you read books, especially books like Gamow and you know, other books from scientists that published these books or papers or whatever, let's say in the 30s, 40s, 50s, or 60s, there was still a large section of the scientific and engineering community that was still putting it out in the centimeter gram second rather than the meters kilogram second. And you can see that from in both of those, the second is the common unit. And as you know from our previous lectures, the second, of course, originally was the heartbeat. And that created a full unified system for their scales and the weights and everything else. I'm not going to necessarily go into that, but you know, I'll take a second. Let's just take a second and go into that for a second. So if I had a stone and I put a stone on I wrapped a rope around a tree limb and I hung the stone from the bottom of that tree limb. Oh, better not use that one. You can't even see that, can you? So let's say I had a tree limb and then I hung a ball from the bottom of that tree limb, and then I started to push the ball so that the ball would go out and back in. So really a full cycle is all the way out and then all the way back, right? That's a full cycle. And so if that swings during one heartbeat, how long is this line? And it turns out to be 94 centimeters. So very similar, that should say 94 centimeters, which is very similar to the meter, isn't it? And so that was the long cubit. So their long cubit and our meter are almost exactly the same. And that, of course, would go out in one heartbeat, come back. And we know that we have approximately today about 70 heartbeats per minute. So if we were going to call that the second, which they did, the second really isn't the same as the second nowadays, is it? In fact, nowadays, if we take the second and we say there's 24 hours times 3,600, we've got 86,400 seconds per day, right? Back then, they really worked more on a day that was probably closer to 100,000 seconds a day, because the second that they looked at was really less than a second is nowadays. There's about, we say there's 60 heartbeats or seconds to a minute, whereas they said that there were 70 heartbeats or seconds to a minute, right? So anyway, let's just go on past that. It seems odd that that camera is constantly trying to refocus, but whatever. So let's get into the dimensions and units. If we do, we come over here, the first thing we're going to look at is area, right? Area, and you probably remember this from the derivation, the class that we had at the very beginning of the mechanics course, if you had me for mechanics. Area is meters squared, right? Because we're using the primary units of length, length times length, pi r squared, however you want to do it, whatever equation you want to use, you're going to end up getting meters squared for area. For volume, same thing, meters cubed. I don't think I have to really explain that to anybody. And then for velocity, using the primary units we have, unit of length, unit of time, then we can go back and say it's the difference in length over the difference in time, or meters per second. And that would be ds over dt if we wanted to write it as a differential fraction. Acceleration, if we look at acceleration, we see that acceleration is just a change in velocity over the change in time, right? Or dv dt. But if we replace v with what we have up here, right? Velocity equals ds over dt, then we get ds over dt divided by dt. Now, when we rationalize that complex differential fraction, what is really being squared here? Is the ds being squared? No. The d's are being squared. So we write it as d squared s over dt squared. I hope everybody can see that, because the dt is still in the denominator, and that dt from the denominator of the numerator goes into the numerator of the denominator, right? Denominator. So we get d squared s over dt squared. I like to point that out to people, because when you get into graduate school, or when you're doing an advanced differential equation course, you know, or when you're reading journals, you're thinking to yourself, why isn't that ds squared? Shouldn't that be ds squared? No, ds squared would be meters squared per second squared. It's d squared s. The s is only meters, not meters squared, right? Now, force. Force, Newton's second law tells us force equals mass times acceleration. Mass times acceleration, meters per second squared, gives us kilogram meters per second squared. We know that there's a nickname for kilogram meters per second squared, and that's a Newton, right? So force equals a Newton. Lay people, you know, call it Newtons. We don't really. We think of force as a kilogram meter per second squared. As engineers, you want to always, you know, go back to the fundamentals, go back to the conceptual underpinnings. So let's go on to energy. Now, if you look at energy, energy has a whole variety of different equations. I picked one equation here, force times distance, because we just derived force's combination of primary units, so I thought I'd put force in here. But, excuse me, if you want to look at energy equations, they would all come out exactly the same combination of primary units, wouldn't they? Mass times velocity squared over 2, that's kinetic energy. L times I squared over 2, that's inductor energy. CV squared over 2, that's capacitance times voltage squared, that's going to be capacitive energy. M times G times H is potential energy. So there's a lot of different equations for energy, but in the end, we all come back to E is going to be equal to kilogram meters per second squared, that's force, times a meter. Well, doesn't that give us kilogram meters squared per second squared? That's right. And that combination of primary units, kilogram meters squared per second squared, we have a nickname for, and we call that a joule. Now, energy and power are also related by time, aren't they? So we could say that power equals energy over unit time, or we could say that energy equals power times time, right? But let's just put our things in here. We now know that energy is a kilogram meters squared over second squared. And we know that time is a second. If I write this out in a more fully fractional form, right, I get seconds per over 1. So if I was to simplify this complex fraction that I have right here, it would be the numerator times the reciprocal of the denominator. We learned that in 3rd grade. Kilogram meters squared over second squared times 1 over second. So what do we get? We get a kilogram meters squared over seconds cubed. That's how you should think of it for the rest of your life. Kilogram meters squared over seconds cubed. I say power, you say kilogram meters squared over seconds cubed. And we have a nickname for kilogram meters squared over seconds cubed, don't we? We call that a watt. Right? So, taking that a little further, I wanted to look at the power equations that we use in electrical engineering. And really, the power equation we only have one power equation. P equals IV. P equals IV. We also have Ohm's law. V equals IR. Really, Ohm's law is V equals IZ. That's the complex form of Ohm's law. where we actually look at Z and we take Z into account. And of course, you're probably thinking, well, what is, why is Z? I'm just reminding you, Z equals R plus JX, doesn't it? So Z is a complex number. And we'd have to understand how all these things interact. But anyway, that's beyond this lecture on dimensions and units right now. I will get into that later on as we start to work through electromagnetic field theory. I just want to point out one thing here, right? If that is Z, and Z is a complex number, then here would be Z's complex conjugate. That would be R minus JX. Does everyone see that? See what the complex conjugate of a complex number is? So if I had a complex number that was A plus JB, its complex conjugate, let's say that's Z, I'll call that D. Let's just say that D is a number and it's A plus JB. Then its complex conjugate, and we usually put an asterisk up to the right of the variable when we're talking about its complex conjugate, and we're going to be using this a lot in this semester, is A minus JB. In fact, in this semester, you're probably going to learn more about working with complex variables than you've probably worked with at any time prior to this. Although I say that, and you know, we have to see how everything is going with the electrostatics. That'd be the first 2 or 3 chapters that we're going to go through in the book. And I'll talk about the book more. I'll send an email out, of course, that's got the syllabus and the book in the syllabus. And we'll have a lecture that talks about the syllabus a bit too. Anyway, let's go on with this right now. So we know it's complex conjugate. We know P equals IV. And we know V equals IR or V equals IZ if we wanted to look at the complex equation. I'm sorry that I'm a little hoarse. I do not have COVID-19, but but this is the second time, really the third time I've done this lecture, and the coffee just isn't keeping. I'm doing all the talking. I mean, in class, I do a lot of the talking, but then I also take a break every once in a while, have a sip of coffee while I have one of you answer one of the questions that I've asked. Well, I don't have you here anymore, so I have to do all the talking. And so I've been doing that for 3 hours, and now we're at the point where hopefully we'll be fine. Now, let's keep going. I want to finish this up. So V equals IR, if we interchange those algebraically in here, that gives me P equals I squared R, and it gives me P equals V squared over R. Well, if I've got P equals IV, and I've got V equals P over I, then isn't P kilogram meters per seconds cubed and I is amps? It's a primary unit. So if I simplify that complex fraction, I end up getting a kilogram meter squared per seconds cubed amp. And for that combination of primary units, we have a nickname, which we call the volt. Excuse me. Now, let's take that a little a step further, because we've got P equals IV, but we've also got P equals I squared R, right? So if P equals I squared R, then doesn't R equal P over I squared? That would give us a kilogram meters squared over seconds cubed divided by an amp squared. And I think everybody can see, just like we simplified the complex fraction for the volt, we're going to simplify the complex fraction for the ohm. And that gives me a kilogram meters squared over seconds cubed amp squared. And we've got a name for that. That's called the ohm, right? An ohm is a kilogram meter squared per seconds cubed amp squared. And so that takes care of our resistance too. And you know, excuse me for a second. We could take this a little further. You know, I did say that E equals capacitance times voltage squared over 2, right? Well, wouldn't that tell us that the capacitance then is going to be equal to 2 times my energy, E being energy, divided by V squared? Wow, that's a big equation, isn't it? We don't really care about the 2 at all. We just care about the energy thing. So that would be a kilogram meter squared over seconds squared, and all divided by the square of a volt, and a volt is a kilogram meters squared over seconds cubed amp. And what I want to do is I want to square that. And you're probably saying, "Oh my God, I better do this in 2 steps." No, really, I'm not that worried about it. So we've got kilogram. Let's just make what I call the major fraction. When we're simplifying a complex fraction, I like to make the major fraction. What goes in the top and what goes in the bottom? Well, I think we can see that the kilogram meters squared over seconds squared, that's going to be kilogram meters squared over seconds squared, right? That's in the numerator, or you know, on the top. And then this is really upside down, because the square is going to square through the whole numerator of the denominator as well as the denominator of the denominator, right? So that would give me a kilogram squared meters to the 4th over seconds to the 6th over amp squared. All right, let's put a parentheses around that. And when we simplify these things out, I think everyone can see that kilogram is going to cancel out with those 2 kilograms. That meters squared is going to cancel out with all but 2 of those meters to the 4th. The seconds squared is going to cancel out with 2 of those, giving me a 4. And so we've got rid of all of those. We got this. And so I get amp squared seconds to the 4th over kilogram meters squared. You're probably saying, "Oh my God, is that the upside down unit?" That's right. That's what I like to call capacitance. I like to call capacitance the upside down unit. Because it's got the kilogram meters squared in the denominator, and it's got the amp squared seconds to the 4th in the numerator, doesn't it? Which is so opposite. If you look back at the volt or you look back at the ohm, it would be upside down. So that's why I call capacitance the upside down unit. And what's the nickname for a capacitor? It's for capacitance. It's a farad. So instead of saying amp squared seconds to the 4th over kilogram meters squared, we could just say the farad. That's going to be the end of the lecture for dimensions and units right now. I wouldn't mind stepping into, talk about inductance and stuff like that, but this is really just a trial to see what type of, if I can keep this under 128. That's been about 25, 26 minutes. So let's see if we can still post this to YouTube, or if I have to post it to my SharePoint on at Wentworth.